our last presentation will come from Thelma Gart, and it's a team deep on data. And they're looking at reducing mineral exploration risk in the Yukon Plateau.
Very happy to be here. I'll be presenting with my colleagues Edward Lewis and Taronish Pitawala. So let's start. So first, the team. We are a global multidisciplinary team of 9 geoscientists, and we were eager to participate in the challenge. Very enthusiastic about innovation and exploration, and really transcended the geographic borders, regularly using web conferencing and data repositories in the cloud. As you can see, I'm from Brazil. I had my colleague also, José Luis in Brazil, Taronish in Canada, Nigel in the UK, and the other guys from the other company, EIGS, also in the UK. So it was challenging by itself to have such a diverse team. And also, we were from different specialities, so geophysicists, geochemists, geologists, software engineer, GIS specialists. So we tried in this way to really have a full integration and different mind settings to work with the data. So we have chosen the Yukon because all data sets that were evaluated, discussed individually, and at the end we selected this one because the available software techniques and experience available in the group was taken in consideration. And the Yukon Plateau, this was recently published in the LinkedIn, so we took this, showing that in reality there is a small number of recent discoveries, so there's more potential in the area. There is a good airborne geophysics, limited geological cover, and a long history of exploration. Data visualization. The Yukon data covers approximately 180,000 square kilometers. It's a very large area for investigation, sparse data. The techniques include 2D data analysis and 3D models, and we have used interpreted the data using 2D plane maps, vertical cross-sections, 3D voxel, and vector voxel slices. And we have integrated the data. In reality, we have taken the different data sets through different workflows. So we have used the geophysics data using the magnetization vector inversion, then 3D SOM analysis, then targets, geophysical targets. The geochemistry passed through normalization, a QA, then principal component analysis, the Varimax analysis, and then targets. And the prospectivity maps using a mineral model yielding permissive areas, favorable, highly favorable areas, and the targets. So we joined all the targets together, and when there were more with higher resolution geophysical data, we have also inverted, did some analysis, and then got the refined targets. And at the end, the final targets that we found. Well, my colleague Taronish will talk about the innovative technologies.
Thanks, Thelma. We'll start with the approach that we took with our geophysical data. So the most widespread coverage we had came from the airborne magnetic field data, which is a potential field measurement, and what we wanted to do is take that potential field measurement and turn it into a 3D volume. To do that, you use geophysical inversion, and the approach that we used was magnetization vector inversion. And the biggest, I guess, benefit to magnetization vector inversion is that it does not make any assumptions about the nature of the magnetization in the subsurface. So conventional susceptibility inversion assumes that all of the rocks in the subsurface are magnetized along the inducing field direction. We know that that is not typically the case. There are many effects, including remnant magnetization, demagnetization, and anisotropic susceptibility that causes the rock magnetization to differ from the inducing field. Magnetization vector inversion solves for both the amplitude and the direction of the magnetization. So there are no assumptions made about induced remnant or anisotropic magnetization. Here is a cross-section that compares a conventional susceptibility inversion that has no bounds on positive or negative susceptibilities compared to a cross-section of a magnetization vector inversion model. So whereas the conventional susceptibility inversion has an inherent constraint that magnetization is along the inducing field direction, the MVI does not have that constraint and returns 4 pieces of information. So the amplitude of the magnetization and then the 3 components or the X, Y, Z components of that vector direction. So having all of this extra information also means there's more to interpret and more to visualize. The approach that we took to help sort through all of the results from the magnetization vector inversion was to use self-organizing maps. And self-organizing maps are essentially a way to take a high-dimensional data set and find patterns or find similarities within domains. And so we used self-organizing maps to help us find domains of magnetization. A lot of those domains were simply background or not anomalous. What we then did was focus on the anomalous domains. For our geochemical data, again, multidimensional, having different types of assay data. So we use principal component analysis to make those, take those variables and find sets of uncorrelated and correlated variables. The PCA and the MVI with the SOM analysis was passed on to a prospectivity analysis system, and here to talk more about that is Edward.
Hi, so yes, I'm going to go a bit more into semantic technology, which is a novel approach to processing geological data. We've heard a lot in this conference about machine learning, and people have name-dropped things like IBM Watson system and Google. The underlying technology, or one of the key underlying technologies behind those systems, is semantic analysis and linked graph data. What these systems allow you to do, or allow the computer to do, they do allow the computer to understand the data that they store and allow them to reason about that information. So this allows a very integrated approach in the terms that you can use qualitative data and quantitative data and analyze them both at the same time in a single database. This allows the geologist to be able to concentrate on building the model they'd like to apply to that data, the mineral systems approach they'd like to apply to that data, without having to get down to the nitty-gritty themselves, in the same way that an automotive engineer designs the car, they don't build the car. This sort of a visualization of linked graph data in comparison with tabular data. So tabular data, your data is stored in doubles. You have a feature and an attribute, and that's it. With your graph type data, it's stored in triples, a subject, a predicate, and an object, such as sky has color, blue, or copper, or a feature has commodity, copper. So the relations are very explicit in the system. And this allows for much faster indexing and faster analysis by the computer. It's also much more flexible in terms of what data you can hold in that system. For a tabular data, you might have to have lots of individual tables that you then join together to run an analysis, whereas with graph data, you can have it all in the same graph. It's also a much more flexible way of storing data. If things about the world change, it's easy to change the relations between objects and still maintain the integrity of your database. Where if there's some fundamental changes and you're using tabular data, you might end up having to change the entire architecture of your database when you want to move ahead or do anything else. So on top of the graph data, which is in RDF format, Resource Descriptive Framework, we can apply knowledge, geological knowledge, to that data via an ontology. So an ontology is a way of teaching a computer that understanding. So we have taught a computer geology and the fact that the computer can now understand what a phyllite is, that it has a fabric, has a grain size, has a metamorphic type. So this is very useful, obviously, for when you're then thinking about your criteria that you're going to apply to do prospectivity analysis. Your criteria may be for looking for a specific metamorphic type. And you can then search for that directly, and it'll understand it needs to look at the phyllite without you having to explicitly enter that data into the system. Obviously, once we've then got our enriched database, we then need to start thinking about what questions we're going to ask that database. We've built criteria for over 50 different mineralization models systems based on peer-reviewed literature from USGS, Geoscience Australia, British Geological Survey, amongst just general journal articles. So these criteria are often, say, qualitative in nature. They're questions, they're ideas. So to be able to apply those ideas directly to a data set without having to transform your data into quantitative data, we find very, very useful, and it's much more transparent in terms of what we're doing. Our criteria then, as these ideas, are converted into SparkQL language, which is similar to SQL, but it's for graph-type data. And it does have a spatial analysis component to that language. You can do that. There's an example behind me. You can look for a specific age, specific rock type, and although you wouldn't normally write SparkQL yourselves, I'm sure you can quite clearly see in that code what we're searching for. It's very human readable and I say, transparent. So we were obviously looking at copper, gold, porphyry. So we had our criteria that we'd identified at a global scale, which they then had to adapt to local conditions and what data we had available locally. Our criteria are scale dependent in the same way that Cam was talking about yesterday. We have our regional criteria, district, and local scale. Unfortunately, because of the resolution of the data that was available to us, we weren't able to identify any local scale prospects, because that would generally be in our system in the order of sort of hundreds of meters square rather than kilometers. But we were able to identify permissive areas and district scale areas. So these criteria, as I say, again, they search that original database and also that enriched database with that geological understanding that's been built into it. This is the input data that we had to work with. So we had the geology and structural information available from the survey, and we also had our PCA geochem that Geosoft had helped us out with, and some interpreted structures also that we brought into the system and then converted into the RDF format. That's actually able to be done with open source software. There's systems for managing RDF data with that. Then the following, where I'm going to break down the process into the component steps, that's just for visualization purposes. When we actually run the analysis, it's a single operation. You press the button once and it ends up at the final output. So these are our permissive criteria. We have tectonic criteria, magmatic criteria. So these are things looking for convergent plate margins, regional scale structures, island arcs, calc-alkaline to alkaline suites. Where these intersect, that would then be our permissive area. And then this is a bit messy, but these are our 7 favorable criteria that we have, which are a mixture of magmatic, structural, and alteration geochemical characters that we're looking for. We then ranked those because there was 7. We were able to be a bit more focused about it. So we had favorable and highly favorable areas, with favorable being 2 criteria from each of the 3 categories, and highly favorable being more than 2 criteria from each of those 3 categories to pick out our favorable areas. And then that's our final output, which is the permissive and favorable areas based on our geological understanding of the data and what's acceptable. That was compared with and validated against the known mineral occurrences. We didn't use known mineral occurrences at all in the analysis or in any of the criteria. We wanted to take a very conceptual approach and not bias the data or bias our analysis into finding things that had already been found. That's quite a capture efficiency on that of 85%. Which we were quite happy with, considering we didn't use that information. Then we passed this analysis back to the geophysics team for 3D analysis, and which I think Thelma's going to continue to talk about.
Thank you. So then we integrated for targeting, and we took all the information together, geophysics, geochemistry, prospectivity maps, and found some targets. So we can have combined the complex data, models, visuals into simple sections and 3D force. So this is the magnetization vector inversion amplitude, and in section, then you have the plan map with the geology, the PCA, and the prospectivity analysis. And at the right, you have the targets in 3D, one of these targets in 3D. So, and this is the SOM analysis. Then, as I said before, where there was available higher resolution geophysics, we have also inverted to test the targets, and then we have drawn the targets and suggested them. So, in our view, the significance of this work to exploration that we are applying techniques that are not previously available to explorers. We have used larger scale inversions, 2D and 3D integration, and semantic analysis of geological data. And as the outcomes, we have proposed 22 drill target areas. So we have an untied 3D magnetization vector distribution of the entire Yukon Plateau magnetic data set, regional scale plan map of geochemical domains, regional scale plan map of favorable and permissive prospective domains, section maps of anomalous zones with proposed drill targets, and we have also confirmed known targets. So we have worked first using the known targets, Coffee, Casino, and Minto, and we have seen that the methodology worked well, so we have go ahead and propose new drill target areas. And that's it. Thank you.
Any questions for Thelma and her team? She's got backup, so don't be afraid.
Set up the team. Well, we are from two companies, Geosoft and IGS. IGS have cooperated before with Geosoft with the Botswana Geological Survey, for instance. So we decided that we could use together the techniques, and we have done this because, well, in Geosoft, we always communicate, the technical teams. So the team from Brazil, myself, José Luis, Taronis from Canada, Nigel from UK, and the IGS team is so, yes, this was also a challenge, so it was fun. Difficult but fun. Yeah.
Anybody else? Look forward to seeing as many of you as we can at the gala, where the awards and big checks will be passed out.
Wow.
Literally, big checks. All right, thanks all the teams.
Appreciate it.